Hello, my name is Jeremy Seek, and this video is about the Deduce proof assistant. And in particular, this will be an introduction to the programming language that's inside of Deduce. Okay, it's a very simple programming language, and we're going to hit the basics of it in this video. So one of the first things you might want to do in Deduce is just to learn how to do some simple things like print a number, or maybe print a numeric expression like 40 plus 2. Okay, so you can just do that simply with a print statement. Though you will need to import the from the standard library the library for unsigned integers. Okay, so in Deduce, when you type in a number like 40, that's an unsigned integer. Okay, so let's go ahead and run this in Deduce. So here we've got this scratch.pf file that we've just created. The Deduce itself is a Python program, so we're running it using Python 3. And indeed, this program prints 42, as you'd expect. You'll see that also Deduce is telling us that that our file is valid. Normally, if you're writing a program, when you run it, it doesn't say whether it's valid or not. What's going on there is that we could have also included some theorem statements and proofs in our file here, and then Deduce would have checked to make sure that they're all correct. Okay, but for this program, it just prints out 42. Okay, so that's just kind of getting started here. With print statements, another thing you can do in Deduce is to create functions. So there's the fun keyword. So let's say you want to do, compute the area of a rectangle, or you know the height and the width. You could write a function like this called area, and in the body of the function, we just put one expression, which is the return value, and we want to just multiply the height times the width. Okay, so there's our area function, and then let's say we want to call the area, and then maybe call this function, and we can call it with arguments 3 and 4, and then let's maybe go ahead and print that out. Okay, so we can see, we're expecting to see it print out 12. Okay. Indeed, there we go. Now we've got our program that prints out 42 and then 12. By the way, here I'm using the Emacs editor to create, to write this Deduce program. But we also have support for Visual Studio, so VS Code. So if you're, we'll have another video on how to install that and get going using VS Code. All right, so we've got print statements, we've got functions. Okay, now we need a way of creating more interesting kinds of data, like compound data in Deduce. And one of the ways to do that is what we call a union statement. So here I'm going to declare some different kinds of fruit. Okay, and we use the keyword union because this is reminiscent of a union in the C language, except that these unions will be what we call type safe. Okay, so you won't be able to misuse these unions. So let's say we have 3 different kinds of fruit. We have apples, we have oranges, and we have bananas. Okay, so there we've declared some different kinds of fruit. And then let's say I want to go ahead and create a value or an object of type fruit. I can declare a variable like this, fruit of, define A, that's a variable name, and I can put whatever fruit I want in it. I could put apple in there. Okay, and then if I print A, of course, now it's going to print out apple. All right, so there we go. We've got apple in variable A. Of course, we could have, another variable B with a different kind of fruit in it, like maybe banana. And there we go. So we've got an apple in variable A and a banana in variable B. Okay. So in some sense, what we've seen so far with our union is essentially the same as what you'd be able to do with like an enum or an enumerated type. But we can go a little bit further. So let's say we wanted to keep track of whether our fruit is rotten or not. And maybe for like apples and oranges don't rot very fast, but man, bananas really rot fast. So what we want to do is attach a Boolean to our bananas to say like whether they are rotten or not. Okay, so now I could define, maybe another fruit. This is now fruit 2, and it's a banana, but maybe it's not rotten, right? So not rotten. Okay, and then maybe we have another, one, B, 3 here, and this one is rotten. Okay, and so we're using this Boolean to store that information. Okay, and if we go ahead and print these out, we'll get the expected thing here. Now, not only do we have bananas, but we only have the fruit 2 type. Right now, we've got this extra information, the false or the true, attached to our bananas. Okay. Now, so that's how you construct data, these union types or union values with the extra data attached. Let's look at how you can use unions. So, for example, let's say we wanted to define a function that that answers the question, is the fruit rotten? Okay, so let's say we've got a parameter coming in of the fruit 2 type, and we want this function to return true or false, depending on whether the fruit is rotten. Okay, so here what we're going to see is a use of the switch statement. Okay, so we can do switch, and you can in Deduce you can do switch on anything that's a union, right? So fruit 2 is a union, so we can go ahead and do a switch on that, and then we're going to have a case for each one of the different kinds of fruit too, right? So we've got apple. We've got, I can never spell apple correctly. We've got oranges. We're going to have to fill in what to do in each of those cases. And we have bananas. And then for banana here, you see it's a little bit different. We've got this R variable. Okay, so this is a pattern variable. And what's going to happen is the fruit that comes in, if it's a banana, it's going to have a true or false attached to it. So that Boolean will then be placed in this variable R, and then down here we can use R. And in fact, that's what we want to do is, is the banana rotten? The R variable is going to say yes or no, whether it's rotten, right? If it's an apple, of course, they don't rot very fast, so false. Orange, those don't rot very fast either, okay? So now we can do something like print is rotten, B2, and print is rotten B3. Maybe also print is rotten apple, right? And what should we get here? We should get, false, false, true, right? So we'll look at what Deduce tells us. Oh, Deduce is telling us that we have a mistake somewhere. I misspelled banana. Fair enough. Okay. So indeed, down here for our last 3 printouts, the apple is not rotten, banana B2 was not rotten, but B3 was indeed rotten. Okay. All right, the next thing I want to get into is recursive data structures. Okay, so suppose we want to represent a linked list. Okay, like here I'm going to draw a picture of a linked list with the numbers 7, 4, and 5 stored inside of that list. Okay, so again, we can use a union to represent this. Let's call it a uint list. And then we're going to need the kind of list that's empty. Okay, so we'll just call that empty. And we're also going to need a node, right, to represent one of these squares. And a node is going to have an integer in it, right, one of these uints. And it'll have the next node, right? That's what the arrow is sort of the pointer to the next node. So we'll have uint list also stored inside the node. Okay. So now we have what we call recursive data structure, right? Because you can have, the same data structure nested in itself, inside of itself a whole bunch of times until you bottom out with an empty. Okay, so that's recursive data. Okay, maybe we'll make that extra. It's an example of recursive data. And now we're going to write a recursive function on that data. So just a good place to start is just the length function. So recursive len for short. It takes a uint list and it's going to return an unsigned integer. Okay. Okay, so when we're writing recursive functions, this is maybe a little bit different from what you might see in Java or something like that. We're going to have, the recursive definition is going to have a number of sort of equations, okay? And we're going to have one equation to handle each one of the different kinds of data that can be of this type uint list. Okay, so for the first equation is going to say, well, what happens if we have length of empty? What should that be equal to, right? And so the empty list has nothing, right? It has 0 elements inside, so the right answer there is 0. And then the next clause here, the next equation, is going to say, what do we do if we have a node? Okay, so what's the length of a node? And then notice this time we have these, again, pattern variables. Okay, so these are placeholders for whatever data is coming in. This node that's being passed a length, it's going to have the actual element, the actual number there, and it's going to have a next node. Okay. And so the way we're going to want to compute the length is, well, we can compute the length of the next node, right? And then we can add one to that, right? So let's say I'm sitting here on this first node with 7 in it. If I call length on that, we're going to then call length on the next, which is on, starting here with 4 and going on. That'll finish off. It'll come back and say 2, and then we'll add 1, and we'll get the right answer as 3 for that. Okay. All right. So let's go ahead and create one of these linked lists. We'll define one named L here. We'll put it in the variable L, and it'll be a whole bunch of these nodes nested inside of each other. All right. So we're building an actual object that matches this picture up here, okay, and putting that object in the L variable. And then now we can, for example, when we call length on L, we should get 3, right? And here we have a chance to sort of bring up another feature of Deduce, which is this assert statement. So if the formula on the right here is true, then the assert does nothing. If the formula is false, then you'll get an error. Okay, so hopefully, basically nothing's going to happen when we run this assert. Okay, actually, we've got all these print statements up here. Let's get rid of those for now. We don't want to clutter our output with all those print statements. So we're just getting rid of those. Okay, and now prints out nothing whatsoever. Okay, so the assert must have succeeded. If we change this assertion to something that's false, then indeed we'll get an error. It'll say assertion failed 3, which is the result of length of L is not equal to 4. Okay, so let's go ahead and put that back to 3, and then Deduce will run to completion and be happy about that. Okay, so that was sort of a simple list. I want to point out that the standard library for Deduce already has a data structure for lists in it, and that data structure is generic, it looks like the following. I'm just going to sort of retype in what the one in the standard library looks like. It looks like this. Okay, so again, it has an empty and it has a node, but it's generic with respect to the type of element in the list. Okay, so we don't actually want to create that here. We can just import the list library, and then we could define another list. Okay, so this time we'll basically do the same list, this time using the generic one. And so we're going to have node 7, node 4, node 5, and then empty. Okay. Node 2. Oopsie. I forgot the equality sign there. Okay. Oh, and I should point out, so Deduce sort of has some special printing to make when you print out a list, it has this nice format. So instead of seeing node, 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 it prints it out as this nice comma-separated list of elements with the square brackets on either side. Okay, we can also use that as input as well. So, I could write, 7, 4, 5. Print out 3, and that's going to work as well. Okay. Okay, so we've got these generic lists. We might want to write generic functions over our generic lists. So for example, there's the length function now for this list, for generic lists. So this length function is now generic, and then it takes a type parameter e. And this one will also, return an unsigned integer. And then basically from here on out, it's the same deal. It's just that, we're generic with respect to e. Okay, so we can write length empty is 0, length of node is, 1 plus length of next, right? So this is what the length function looks like in the standard library, and it's a good example of how you might write your own recursive functions over generic data. Okay, and so now let's see. We can use that length function just as you would any old function like that. And, we get the right answer here, that the length of L3 is indeed 3. I want to show off one more feature of Deduce. We have not yet talked about if statements. And of course, Deduce has if statements. So you could say something like, if length L3 is equal to 3, then 42, else 0. So this would be a perfectly fine print statement, and indeed this is going to print out, 42. Okay. Oh, actually, so when I said if statement, that was a slight inaccuracy here, right? So here, this is really a conditional expression, right? So you have the condition, but then the two branches are each just going to be an expression, and then the result of one of those branches is going to be the result of this if expression. Okay, so like in Java or C++, this would be written as it would be like using this ternary operator with the question mark and the colon. Okay. One other thing to emphasize here too is that in C++ or Java you use the double equals to mean equals. In Deduce you just simply write equals for equals. Okay, so let's kind of put these different pieces together to sort of see a non-trivial function. Let's write a function that does a search over a list, looking for a particular element and returning the index of that element. Okay, so here we have a recursive function that actually takes two parameters. The first parameter has to be a union. And okay, so this is sort of special here. And you have to pattern match on that first argument. Okay, so we really have to say search of empty, and then we've got our second argument is just going to be we're just going to use a parameter y for that. And so if you're searching for y, but you've got the empty list, we're going to return the index 0, which is sort of like past the end of the list. Okay, that's how we're going to indicate that we could not find what we were looking for. Okay, let's say we have a node that has the element x in it, and then the rest of the node, the rest of the list is xs there. And then we're still looking for y. And okay, now we need to say, how do we search when we've got a node in our hands? And okay, here's where we need an if statement. We need to say, okay, is y equal to x? Is x the one we're looking for? Okay, because if it's true, then we want to return the index for this x here. And the index, well, this is at the front of the list, so we just want to return 0. Okay. Now, if x is not the one we're looking for, we want to keep searching, right? So we're going to search the rest of the list, xs, for y. Okay, and that's going to give us the index of where it found y with respect to the rest of the list, but we want to return the index for the whole list, so we really want to add 1 to that index here. Okay, so now we've finished our search function. And let's say we go ahead and do a search for, we search L3 for the number, L3 there. Let's say for the number, for the last one, 5, okay? 5 up here in this list is in position 0, 1, 2. It's in position 2, so this should give us back 2. And indeed, we did not get an assertion failure, right? Let's get rid of some of these print statements as we go along here. Okay, and let's try searching for another. Let's try searching for something that's not there, right? Let's say we search for, we've got 7, 4, and 5. So let's search for, 3. 3 is not there. We should get back an index 1 past the end, right? So 3 should be our index for that. Good, that succeeds. Let's do another one. Let's say we're searching for 7. That should be at position 0. And that worked great. Okay. So that's where we're going to end for today. We've seen some examples of how to write functions in Deduce, how to create some data using the union feature, how to write some recursive functions, and also we've looked at some generic unions and generic functions. And that's where we'll stop for today.